We physicists have waited 100 years since 1916 for this photograph.
For decades, black holes have been the universe's ultimate locked rooms. Nothing goes in, nothing comes out. But now, theoretical physicist Michio Kaku says new data from the James Webb Space Telescope may be giving scientists their first real clues about what's happening inside these cosmic monsters. One of the most famous examples sits at the center of Messier 87, a galaxy about 50 million light-years away. That single black hole weighs billions of times more than our sun. It literally holds its entire galaxy together. Kaku believes black holes may be more than cosmic vacuum cleaners. They might also be windows into how the universe truly works. How scientists first confirmed one. Since black holes emit no light, finding one is a bit like trying to spot something invisible. So scientists had to get creative. NASA researchers focused on the core of Messier 87 and noticed something strange. A massive cloud of superheated hydrogen gas was spinning around an unseen center at more than 1,000,000 miles per hour. Normally, gas moving that fast should fly apart in every direction, but this gas stayed locked in place, circling something incredibly dense. That was the giveaway. Only one thing could keep matter trapped while moving at such extreme speeds: a supermassive black hole. By tracking how that gas behaved, scientists were able to calculate the mass of the invisible object at the center. The number was staggering: billions of suns packed into a region smaller than our solar system. This was one of the first solid confirmations of a supermassive black hole, and it completely changed astronomy. Black holes went from theoretical curiosities to proven cosmic giants. Today, astronomers use similar techniques across the universe, watching how stars and gas move, letting gravity reveal what light cannot. It's detective work on a cosmic scale, and every discovery brings us closer to understanding how galaxies, including our own, are held together. Roy Kerr's radical idea. Here's where things start getting really strange. New Zealand mathematician Roy Kerr took Albert Einstein's equations and asked a wild question: what happens inside a spinning black hole? Kerr discovered that rotating black holes might not collapse into a single point. Instead, they could form a ring-like structure. And if that's true, something remarkable follows. Objects falling in might not be crushed instantly. In theory, they could pass through this ring and enter a tunnel in space-time called an Einstein-Rosen bridge, better known as a wormhole. On the other side of that tunnel, possibly a white hole. A white hole would be the exact opposite of a black hole. Instead of pulling everything in, it would push everything out. Matter enters the black hole and could emerge somewhere else entirely, maybe even in another universe. It sounds like science fiction, but Kerr's math works on paper. Whether nature actually allows this is another question. Still, his idea opened the door to one of the most mind-bending possibilities in physics: that black holes might not be dead ends at all. So what exactly is a wormhole? Think of it like folding a piece of paper. Two distant points suddenly touch. That's basically what a wormhole does with space. Instead of traveling millions of years across the universe, a wormhole could let you jump from one place to another almost instantly. The idea comes from equations developed by Albert Einstein. On paper, these cosmic shortcuts are totally possible. They could connect distant regions of our universe or even link entirely different universes. But there's a huge catch. Physicists believe wormholes would be wildly unstable. The moment one forms, intense radiation and quantum chaos would likely cause it to collapse. Any spacecraft or person trying to pass through would probably be ripped apart by subatomic forces before getting anywhere. That's why wormholes remain theoretical. They exist in math, not reality, at least for now. Still, their existence keeps showing up in serious physics papers, which tells us something important. The universe might allow shortcuts through space and time. We just don't have the technology or understanding to prove it yet. So while wormholes sound like sci-fi portals, they are rooted in real physics. The problem is surviving one. Now here's where things flip completely upside down. According to Michio Kaku, a white hole is the mirror image of a black hole. If nothing can escape a black hole, then nothing can enter a white hole. Instead of swallowing matter, a white hole constantly ejects energy, light, and particles. Imagine a cosmic fountain that never turns off. In theory, white holes could be connected to black holes through wormholes. Matter goes into a black hole here and comes blasting out of a white hole somewhere else. Sounds incredible, right? The problem is that no one has ever observed a white hole, not even close.
Every telescope, satellite, and space probe has failed to find clear evidence of one. Some physicists argue white holes might exist only for tiny fractions of a second at quantum scales. Others think they are mathematical artifacts that don't exist in nature at all. Still, Kaku and others keep them on the table because the equations allow them. And in physics, if the math permits something, scientists take it seriously. This is where modern science runs into its biggest headache. Black holes, wormholes, and white holes live at the intersection of two very different worlds. On one side, you have Einstein's gravity, which explains stars, galaxies, and cosmic motion. On the other, you have quantum mechanics, which governs tiny particles and subatomic behavior. The problem? These two systems refuse to work together. Gravity handles the big stuff beautifully. Quantum theory dominates the microscopic world, but when you try to combine them, everything breaks. Even Einstein himself and quantum pioneer Werner Heisenberg tried and failed to unify these frameworks. Black holes force both theories to collide. At their cores, gravity becomes infinite while quantum effects explode. Our equations simply stop making sense. That's why scientists still can't fully describe what happens inside a black hole or whether white holes are real. We are missing a deeper theory that connects everything. Until that happens, these cosmic mysteries remain just beyond reach, sitting right at the edge of human understanding. At the heart of all this is one huge goal in physics: finding a theory of everything. Right now, we have two extremely successful rulebooks. Einstein's gravity explains planets, stars, galaxies, and even the expansion of the universe. Quantum mechanics explains atoms, particles, and the strange behavior of the microscopic world. Both work incredibly well on their own, but they refuse to merge. When you try to describe what happens inside a black hole, both theories are needed at the same time. Gravity becomes unbelievably strong, while quantum effects become unavoidable. And when physicists plug both into the same equations, the math breaks down. That's why wormholes and white holes remain unresolved. To truly understand them, scientists need a single framework that explains both gravity and quantum physics together, seamlessly. A real theory of everything would not just explain black holes, it would describe the birth of the universe, the nature of space and time, and possibly whether other universes exist. Until that theory is discovered, we are working with incomplete maps. We can see the edges of the mystery, but not the full picture. One of the strongest candidates for that missing theory is superstring theory. Instead of treating particles like tiny dots, superstring theory says everything is made of incredibly small, vibrating strings. Electrons, quarks, photons, all of them are just different vibration patterns of these fundamental strings. Think of it like musical notes. The same string instrument can produce many sounds depending on how it vibrates. In this view, the universe is more like a cosmic symphony than a collection of solid objects. Here's where it gets even stranger. For the math to work, these strings cannot vibrate in just 4 dimensions. They require 10 dimensions. We experience length, width, depth, and time. Superstring theory says there are 6 additional hidden dimensions curled up at scales too small for us to detect. Those extra dimensions allow gravity and quantum mechanics to fit together mathematically. In theory, This framework could naturally allow wormholes and even white holes to exist. It's elegant, it's ambitious, and many physicists consider it beautiful. The challenge is proving it. For all its elegance, superstring theory has a serious issue. There is no direct experimental evidence for it. We have never observed extra dimensions. Every experiment so far describes reality using the familiar 4 dimensions of space and time. Particle accelerators, space telescopes, and precision measurements all confirm existing models without requiring 10 dimensions. The mathematics behind superstring theory is incredibly complex and powerful, but without measurable predictions, it remains theoretical. Do you think we're getting closer to proving other universes exist? Let us know what you think in the comments. See you in the next one.